Today I want to look at density curves and z-scores. So go ahead and turn into your study guides to the notes for density curves and z-scores. Now, a density curve can be created by smoothing the histogram of data. So if we have a histogram of data, we can smooth it out and create what we call a density curve. Density curves always lie on or above the horizontal axis. So when we graph density curves, they'll always be graphed on or above the horizontal axis. The area underneath all density curves is always equal to 1. And later on we're going to look at density curves in relationships with probability distributions and realize that the total probability or area underneath a particular density curve will always be equivalent to 1. A density curve is an idealized description of a distribution of data. Density curves definitely tell us the specifics of our graphical displays. And when we talked earlier about the importance of all the attributes of our graphical displays, center, shape, spread, unusual occurrences, density curves will definitely help us and allow us to be able to describe the features of these particular distributions. The area within a range of values on the density curve basically describes the proportion of observations that lie between those values. And we're going to see in the case of almost all our density curves here that we're dealing with continuous data. And when we want to begin to find probabilities that data falls within a certain range of values, then we're going to take a look at the area within the range of those values underneath the density curve. And that basically will give us the proportion of observations that lie between those particular values, and accordingly will give us a probability associated with that. The mean of a density curve is denoted as mu, and the standard deviation is denoted as sigma. Once again, when we refer to density curves, we're really referring to the distribution of the entire population. And because we're dealing with the distribution of the entire population, we're using parameter values for our mean and for our standard deviation. So the mean of a density curve, once again, is denoted as mu. That's the Greek letter for lowercase m. And the standard deviation is denoted as sigma, the lowercase Greek letter for s. So mu and sigma, once again, denote the mean and standard deviation of our density curve. Now let's talk about z-scores. All normal distributions are the same if we measure in units of size about the mean as center. And changing to these units is called standardizing. Now, if x is an observation from a distribution that has a mean of mu and a standard deviation of sigma, the standardized value of x is called a z-score. We're going to calculate a z-score with the following formula. Our z-score is equal to x minus mu divided by sigma, where x represents the actual observation, mu represents the mean of the distribution, and sigma refers to the standard deviation of the distribution. So when we're standardizing scores and placing everything basically on what we would say the same bell-shaped curve, we're coming up with z-scores. And z-scores basically tell us the relationship that an actual point is from the center of our distribution, from the mean, in terms of the standard deviation of the distribution. A z-score basically tells us how many standard deviations away from the mean an observation lies. And once we place all of those values, our original values, which is what we'll call our x-scores, into converted z-scores, the z-scores will now tell us once again how many standard deviations away from the mean an observation lies. And now we can start comparing multiple different types of normal distributions or bell-shaped curves based on this standardizing value called a z-score. Let's take a look at an example here. Suppose that SAT scores for 1.4 million students in a recent graduating class were roughly normal, with a mean of 1,026 and a standard deviation of 209. Now, ACT scores for more than 1 million students in the same class were roughly normal also, with a mean of 20.8 and a standard deviation of 4.8. Now, suppose